In today's Tiny Methods workshop, we'll be talking about some practices for good data hygiene. So first, why is it important? One aspect is quality. You may have heard the phrase before, garbage in gives you garbage out. So we cannot expect quality results and conclusions if the data themselves are full of errors. If we would like good results, good conclusions, which I think is something all of us strive for, we need to have data that are a solid, clean foundation to begin with. Another aspect is productivity. So we can develop some habits for working with our data and protecting our files that streamline our work and prevent questions like, is age 2 or age v2 or age fixed the variable I meant to use? I'm sure a lot of us have come up against that before. We've created variables. We think we'll remember what they are or why they're different from similar variables, and then we don't. And we either have to recreate the variables or try to dig through whatever we did document in the past about creating these variables to figure out which one we actually intended to use in our analysis. And you do not want to have to redo days, months, or even years of work because you can no longer make sense of your earlier files, or if your computer decides to just give up on you right before that critical deadline. And it's always right before the deadline, right? Another aspect is communication. So facilitating communication of your work to others. So indicating what did you do and how did you do it, which is particularly important if you're working in collaboration with others. And also reproducibility. So you may have heard of the reproducibility crisis or the replication crisis, which is an ongoing crisis in which it's been found that many scientific studies are difficult, if not completely impossible, to reproduce, which is not good. It's not something we strive for. So if given your data in your script or code files, could someone else independently reproduce your findings? They should be able to. The data should be clean enough that they can go ahead and run your script files and get the same output that you did. And it should also be documented enough that they can follow the steps that you did to arrive at those results. One strategy to practice good data hygiene is to protect your raw data. So never modify your raw data. Keep that separate so you have your original data file in a safe location that you do not change. So this file may serve only as input in any analysis, and ideally you may have this file serving as input, but you also have an additional backup stored elsewhere that never gets touched. So don't change names, add new variables, delete cases, etc. from this original data file. Keep it protected. Then when you do need to make changes, you want to add new variables, delete cases, that kind of thing, create and save a new data set from your original when making such modifications, and then save this file with a new name in a location appropriate for writable output, so things that you can change. As an example here, this is a little bit of code from R. Next to that first right arrow, there you can see between lines 1 and 2. So this is the original data set, and you can see I put in caps, do not modify. So this original data set is called music data 2020. It's a CSV file that's saved on my desktop. So this file will never be modified. It is just serving as input here. I'm reading in the CSV file and I'm storing it as music data. Then you'll see on line 5, I'm creating a new data set. This is a data set that I will modify. So you can see how I'm going to modify it. I put in caps, contains new age category variable. We'll talk about that more later. But here on line 5, I'm copying my original data set. So I'm not working with the original file. I'm going to copy it into a new one, which I'm going to call music data _ AC added. And then you'll see on lines 14 and 15, I'm writing out this modified data set. So my original data set, music data 2020, is still completely untouched on my desktop. This new file will be music data _ AC added, and you'll see that's also saved in a new location. It's under desktop/output. So I know this output, it's things I've created. It's a data set now that I've modified. The original, again, is protected in its own place. It's just straight up on the desktop right now for convenience, but ideally you'd have a designated folder for a particular project where you keep things organized. But for this example, it's separated by itself on the desktop. Then in this output folder, which is where I keep modified things, that is where this new dataset, music data _ AC added, is being saved. The next practice that we're going to talk about for good data hygiene is recoding conscientiously. So do not overwrite original variables when you're doing your recoding. So don't take an age variable, change something, but not give it a new name. Just save it as age again. Instead, create a new variable with a new name. And it's ideal to make these new names succinct but descriptive. So they're short, so you don't have to type out a whole lot when you're writing code, but also they tell you something about this variable. So as an example here, when we're recoding a continuous age in years variable into categories by decade, so 20 to 29, 30 to 39, 40 to 49, 50 to 59, that sort of thing. So do not do this with just age to age. Instead, try something like age to age cat 10. So the first part in blue there, that age, it indicates which original variable the new one came from, so age. So we're kind of keeping a record of which original variables informed our new variables. But we are doing a change here, so we need to indicate that. And then in the second part, this cat 10 tells me that this is what's new in this variable. So it's categorized by 10-year increments or decades. There are, of course, different ways to name your variables. You kind of develop your own sort of style, but it's important to be consistent and to try to be, again, as descriptive as you can in the variables that you're creating. So continuing with our example here, returning back to our code, we can see on line 6 here, this is where I'm actually creating that new age category variable. And you'll see that I'm creating a new variable here, which music data underscore AC added, $, and then the variable I'm creating is after that. It's the little arrow that's pointing up, age cat 10. So we're creating a new variable called age cat 10. And how we're creating it is the part on the right-hand side of that arrow. What we're doing is breaking up the original age variable by these called out breaks here. And in case you're curious why the lowest range of ages here is 20 to 29, the highest is 60 to 69, it's something that I know from working with this data set. The lowest observed age was 21, the highest was 66. So these breaks here allow us to encompass the full range of observed ages in the data set. So after you've created a new variable, it's important to check that that variable was actually created the way that you wanted it to be. So are 30-year-olds appropriately in that 30 to 39 category? And some ways to do this include checking old and new values side by side, which is easy to do, particularly when you have a small amount of cases to check, or making use of graphs and tables, which is definitely advantageous when you have a large data set that you're working with. And we'll see an example of both of those. So returning to our example here again, we can see on lines 12 and 13 here that we're going to check this new variable that we've created. So again, we created that age cat 10. What we're going to do here in particular is look at the original age variable next to the age cat 10 variable that we just created. And the output from running line 13 there gives us the following. So you can see down this first column labeled age, we have the raw ages themselves, and then age cat 10, we have the categories that we've now grouped them into. And looking at line 1, we see 23 is appropriately in the 20 to 29 range, 33 is in the 30 to 39, 42 is in the 40 to 49, and so forth. So we can see that the original ages are now into their appropriate categories in the new variable that we created. So this was an example of checking the old and the new values side by side. We'll see an example of using a table in a moment, but before we do that, let's talk a little bit more about knowing our data. So watch for valid sample size changes when you're creating a new variable. So if you know for sure in your data set that there are no missing values on a particular variable, so then why did the n drop from 100 to 95 after recoding? Clearly something happened here to where missing values were created from the operation that was performed to create the new variable. So double check the code there for errors. It's also very important to know how missing data are coded in your data set. So for example, is a 99 a valid value for the variable at hand, or is it a missing value code? This is something to be particularly aware of when you're using greater than or equal to, or less than or equal to conditions when you're recoding. And we'll see an example of this in a moment. So in this table, on the left-hand side here, we have our original variable. It was called health insurance. And then on the columns, this is our new variable that we've created. It's a dichotomous indicator of whether someone has health insurance or not. So take a moment to look at this table and see if you notice any issues. Okay, so you may have spotted it here. So we can see that a value of 1, or yes, on this new health insurance I variable, which I'll talk about the naming of that in a moment, was assigned to those with values greater than 0 on the original health insurance variable. So whenever someone was coding this, perhaps they thought, okay, no on the original will correspond to no, or 0 and 0 on the new variable. And we have 2 yes categories on the original. We have yes through employer and yes self-purchased, and those are 1 and 2. So if I just use something greater than 0, that will capture 1 and 2, right? And that will then be yes or a 1 on the health insurance I variable. Unfortunately, if they didn't notice that no response is coded as 9, so 9 here is a missing value, then that's going to be captured in that greater than 0. We're going to have 1, 2, and 9 all grouped together as yes. So what we've done now is take a missing value on our original variable. We've created a yes valid observation on this new health indicator. So again, that's something just to be very aware of, how missing data are coded and what that means for recoding into new variables. And like I mentioned, I want to go back to the name of health insurance I there. This little I at the end is telling me that this is an indicator. It's a yes or no. Yes is coded 1, no is coded 0. That's just a convention that I use. Again, you'll probably develop your own style for how you want to name variables, but this tells me that this variable came from the original health insurance. It's different now, however, as it is an indicator with yes is 1, no is 0. And then what this table should look like if recoding was done properly, we can see here now that this health insurance original 9, no response, is appropriately coded as missing or NA on this health insurance I. So again, this is what this table should look like if recoding was done properly. Okay, so the next thing we're going to talk about is using syntax. So do use syntax instead of relying on point-and-click menu options. There are a few benefits to doing this, and we'll talk about some of them here. So it does enhance reproducibility, so there's no need to try to remember exactly what you did to recode a particular variable or perform a specific analysis. Instead, all of that is documented directly in the code for you. It does also save time in the long run. Yes, there may be a little bit of a learning curve as you learn the new syntax for a particular program, but once you get over that initial hurdle, it will help you save time. So if we think about a few ways that this may manifest, so you can easily modify a line or two of code when a small change is needed versus clicking your way through all of those menu options again. You can also recycle syntax that you've written previously. So if you're doing a task that you do a lot, you can prevent a great deal of tedium by just copying and pasting that same section of code and then changing it for the particular scenario at hand. So maybe replacing a variable name. This is versus clicking your way, say, 50 times through the same menu options, changing a little bit each time. And using syntax does allow for greater flexibility. So there are some things that you might like to do that are just simply not available using the program's menu options. So for example, suppose that someone has proposed a new model fit index that you really want to use in your project, and that's just not available in menu options for current software. Then you're going to need to write the code yourself to calculate that particular index. And then some additional tips for using syntax. So describe the steps in the analysis in plain English, or another language as appropriate, at the beginning of the script file. So this is documenting what this particular file does in language that anyone that comes across it can understand. So this can be helpful not only for others, such as collaborators who may not be familiar with the particular syntax that's being used, but this can also be helpful for yourself, particularly when you're returning to this work after time away. So when you're really immersed in a project, you may be sure that you'll remember the steps that are needed or the things that were completed, but if you have multiple projects going or this one gets interrupted for some reason, it can be quite difficult to sort of resituate yourself when you're returning to a project. And this little description at the top can really help with that. And it does also provide a roadmap for where you're going during the coding process. So as you're actually writing the code, you can follow along with this plan and sort of check off, yes, I've done this part, then I need to do this part, I need to do this part, that sort of thing. It's also important to document the code liberally. So will you remember what a particular line of code does, or why one option was chosen over another in a particular analysis next month, let alone next year? I certainly won't. So when in doubt, add a comment. When not in doubt, also add a comment. This really just helps to document what's happening in each piece of your code. And be sure to also record which version of the software you're using. So things do change between versions. For example, a function that worked in a previous version may no longer work in a later version. So it's important to note which version you were working with when you wrote that particular code. And be sure to also include software and version information in whatever your final product may be, whether that be a manuscript or a poster. Do note which software you're using and which particular version you were using. Then returning to our little example for the last time here, I added red arrows to point to all the places where comments were added to this code. So we can see one, it's sort of like each major break for lines 1 and 2 that calls out that this is the original data set, do not modify it. 4 through 11, this is where we're creating and modifying a data set, we're adding that new age category variable. 12 and 13, this is indicating that we're checking this new variable, we're making sure that the ages fall in the appropriate categories. And then the last one's 14 to 16, we're writing out some modified data here. And then on the right hand side with that little diagonal arrow, that is calling out what is happening on each of these lines. So overall in line 6, we are creating a new variable that has the age categories by decade. Then we can see what those breaks are going to be. They're going to correspond to 20 to 29, 30 to 39, etc. This include.lowest equals true. This is going to make sure that 20, if there was anyone with a particular observed age of 20, they would be included in that lowest category. It wouldn't be 21 to 29, it's going to be 20 to 29, so 20 inclusive. And then also we're going to label our groupings on 9 through 11 there, and those are the corresponding labels. So this is telling us what each line of code does, what it achieves. Then finally, let's talk about data storage and preservation. So you've invested a lot of time to make sure you don't modify that original data set, that when you are working with new data sets, you're doing so in a way that your data are clean, things are recoded appropriately, missing data aren't all of a sudden treated as valid values. You've gone through all those steps and you don't want to lose that work that you've been investing your time in. So it is important to back up your files. So have and execute a plan for protecting your work and develop a plan that you will actually follow. So it may be nice to say, I'm going to back up all of my files every hour when I'm working. And that may be feasible. And if that's something that you can build into your habits, go right ahead and do that. But it may also be that perhaps you'll back up all of your files in the evening right before you finish work. That's something that can also be built into your habits. So really just develop a plan that will work for you and that you can actually do. Then it's also important to save your data in multiple formats and multiple locations. So this can be on your local computer, an external hard drive, a cloud service, or even two. So again, just save your data in multiple ways, multiple places. And do be aware of storage requirements for sensitive data. So if you're working with particular types of data like patient health records, those do have very strict guidelines of where they can be stored and how. So make sure you're aware of those. And finally, archiving your files. So this is for long-term storage of files that are no longer actively used. So once you've completed your project, for example. And something to keep in mind here is the aging of hardware. So if you're saving things on external hard drives, those don't last forever and they will need to be regularly replaced. So make sure to attend to that so you don't lose the data that you've stored for the long term. And also consider options like the Scholarly Data Archive at IU. If you'd like more information on that, I did include the link here for you to check out. Thank you for joining me for this Tiny Methods workshop. If you'd like to check out our website, it's on the screen for you here, education.indiana.edu/research-help. And if you would like to contact us by email, it is drhelp@indiana.edu. We are currently pausing consultations for the summer of 2020, but we will be back in the fall. So feel free to check out our website and get in contact with us.